let us briefly revise this case because few of them were not there last day. So this is one of the very interesting cases where the case of continuum equilibrium point. Continuum equilibrium point means you cannot find out this type of isolated equilibrium points. That is the case. Here, those who were last day, they found that is all the points on the Z2 axis, they will be the part of equilibrium point. So that's why we call it as an equilibrium subspace. Happens here, the concept is that as if you have this point, immediately close to that you have this point, this point, this point, this point. Like one after another you have all the points, and in between you have many other points. So that's why you cannot create any neighborhood by which you can differentiate between 2 points. So that's why all the series of points, as I said, like it is not that here like the space of my drawing is limited, so that's why I cannot draw the even points within that zone. So this is the case of a continuum equilibrium point where that is like maybe infinite number of equilibrium points, they are within one zone. Here the zone is entire Z2 axis, and you cannot draw any the epsilon neighborhood with respect to those different equilibrium points so that you can differentiate between 2. So that's why in this case you cannot like separate all these equilibrium points. So the concept of isolated equilibrium points doesn't exist in this case. Rather, here it is the concept of equilibrium subspace. Right? That means if it is a one line and whatever like all the points on that line, they are the equilibrium points. But if it is on the line itself, then you cannot distinguish between the points on that line. So it is a subspace, that is it is a one-dimensional subspace. That's why it is called a equilibrium subspace. No isolated equilibrium points. Okay? How did we draw it? And if this is the situation, then of course the solution for Z1 would be Z10, and for Z2 it would be Z20. Like you consider any of the initial points, like suppose Z10, Z20. If this is the point Z10, Z20, both of them positive, then in which direction it will go? For that we have to check that what is the trajectory of Z1. Z1 will always be decaying because in that case I can consider lambda negative. Okay. So if you start from this point, Z10, 20, both of them positive, and Z, what would be the trajectory for Z1t? Starting from the initial condition, for example, if you consider this is 1, starting from 1, this will ultimately go to 0. So that's, but keeping the other axis, like keeping Z to 0, it is constant. Here this is no time varying term. So whatever trajectory, like whatever phase trajectory you draw, that will go in parallel to the Z1 axis. Right? Are you understanding? So this is like the initial point, Z10, 20, it can be this point, this point, this point, or this point. It can start from this point as well, not a problem. Then for all the positive points, what will happen, that is starting from Z10, gradually it will decay to 0, right? So that's why I am drawing like this, where it will stop after coming here. Because we cannot do anything with Z2, because that is a constant term, Z20, right? So for whatever initial condition you choose, finally it will be attracted towards the Z2 axis. Now here what I have drawn, you can distinguish between these 2 points, but in between these two there are infinite number of points. Like if you consider an interval like this one, like suppose point 1 and point 2, to us it's a very small range, but even we can think about infinite number of points within this interval, isn't it? So that's why here at this moment the picture may seem to us that we can differentiate between the points, but in reality it is not. Even within this small gap you can think about an infinite number of points. So that's why this whole Z2 axis is the equilibrium subspace, and that is the case of continuum of equilibrium points. Okay, so if you choose this side, it will go towards this. If you start from the negative side, that means where Z1 is negative, then what will happen? It will be like that, starting from that is minus Z1 0. So it will also, like if you prepare the table, minus 1, minus 0.9, minus 0.8 up to 0, right? So that's why the direction is in this side. Similarly, for these initial conditions and these initial conditions, always here in this case the Z2 is a attractive equilibrium point, right? And if you consider Z10, only in that case you will be getting the points on Z1 axis, depending upon the value of Z20. So ultimately what is happening? This entire Z2 axis is the equilibrium subspace, right? This is the case of continuum equilibrium points, and this is attractive in nature. So as long as there is one zero eigenvalue, it is still attractive. Although not asymptotically stable, but this is one of the cases of marginal instability, but it is still, the nature is attractive. Okay. Let's see in this case what happens. That is here. Are you understanding why I am randomly putting the dots? What I mean? Why I am putting so many dots? here the whole space is the equilibrium subspace. Why? Because you see there is no movement. Wherever you pick a point, z10, z20, whether it is this, whether it is this or this, there will be no relative movement, right? One point itself is the phase trajectory for that equilibrium point. Sorry, for that initial condition. So this whole space Z1 versus Z2 is the equilibrium subspace, or in this case that whole two dimension Z1, whole Z1, Z2 plane is the equilibrium subspace. Another case of continuum equilibrium point. Here also you cannot distinguish between two equilibrium points, right?
Sir, as I had said in the last class itself, A matrix is 0, then there is no system which is there, right? Technically. If there is no dynamics, A matrix is 0, actually there is no system.
It may happen that is, suppose you have a two input, two output double integrator system.
Okay.
Then the A will be like that only. You think about, like, suppose feedback linearized version of unicycle. Then it would be 1 by S, 1 by S. Ux Uy, and then it would be Px Py. If you now write down its A matrix, it would be 0, 0, 0, 0. And B matrix would be 1, 0, 0, 1. C matrix will also be 1, 0, 0, 1. Usually what you were thinking about, that is like two decoupled system, each one of them having their eigenvalues on the 0. Actually that is absurd, right? Completely decoupled, there is no interaction, so that is only theoretically possible. But in that case, this situation can happen. Two input, two output, double integrated system, and that too feedback linearized.
So in that case, x dot will be equal to u directly.
Exactly. But for a single system, have you understood his question? That is, he was asking that in this case, like 0, 0, 0, 0, completely a null matrix. Is it ever possible to appear in practice? It seems not, but in such cases it can appear. The unicycle mobile robot, that is that it is a nonlinear model. The equations I hope you have already seen. X dot equals to v cos theta, y dot equals to v sin theta, and theta dot equals to omega. If you apply feedback linearization, then it is possible to transform it into a two input, two output double integrator system. In this case, the A matrix would be 0, 0, 0, 0. But at the same time, your B matrix would be 1, 0, 0, 1. Similarly, your C matrix would also be 1, 0, 0, 1. But here, what we are doing, that is the case of double integrator system. This is, you see, this is not a double integrator.
Shouldn't be D matrix would be 1 C matrix.
But if you don't write the C matrix, then how would you get Px and Py? The position, like a single integrator system, x dot equals to u, right? It is something like x dot equals to ux and x y dot that is equals to uy. That is the system. There is no question of D matrix because no feed forward term. And this is the case of, see, this is what I was saying, that this is not a double integrator. although we have two 1 by s terms, but they are appearing independently. So this is a case of 2 input 2 output double integrator system. But here when you write 0 1 0 0, that is a case of double integrator system, but single input single output. And this is a case of T2. That is the difference. So in this case, can anybody tell me that is what will be the shape of the phase trajectories? थोड़ा सोच के बताओ. So in this case, there is Z10, Z20, both of them are constant, initial condition. Then what will be the shape of the phase trajectories? That is like let's take any of the points. Say for example, if it is here Z10, Z20, both of them positive. Suppose this point or even this point, anyone, this point. Then what will happen? T will count positively. T cannot be negative, right? So starting from any point, say Z10, that is a constant term, plus Z20 into T. So starting from any of those points, it will be like this. Isn't it? If the point is this side, or if it is on this,
So it depends on whether Z2 not is positive or negative.
like if the point is here, it will also go like this. Because see the rate of change.
Whose side to go that way? Left side. If Z2 not is negative, Z1 not is going in the negative direction.
Z1 not is in the negative direction.
No, but here it's positive. Z2 is positive.
Yeah.
So it will go right side. It will go right. Z2 positive.
Z2 is
Here Z2 is positive.
Here, that is in
Yes.
both these planes, Z2 is positive, right? That's why I am drawing this direction. Z10 plus Z20 into T.
That's why.
So for this entire plane, your Z20 would be positive, right? But it would be always be diverging. That is, whatever, like it is not attracted towards any point or any axis. Whatever initial condition you choose, that is, it will, all the trajectories, they will always keep diverging, right?
third and the fourth quadrant.
From third and the fourth quadrant, suppose now this case, if the point is here, Z10, Z20, both of them negative, then it would go like this. Now, if you start from this side, this is also another continuum, because like whatever the point you choose, any point you choose, and then from that it will keep on diverging. If you have any doubt, please ask me. So if you have two poles on the origin, double integrator, it cannot be marginally stable. It has to be unstable, and that is the nature also says that only, right? Whatever may be the initial condition, you are choosing, the phase trajectories will keep on. That's what it is, a kind of repelling trajectories or repelling equilibrium.
Condition is on the Z1 axis, then it will stay like that.
If it is on the Z1,
Z20 equal to 0.
if Z20 equals to 0, in that case it would be continuously, it will keep lying on the Z1 axis, right? Do you remember those who had this E601? In case of double integrator consensus, we derived the whole thing. And then we learned that is if Z20, if the initial condition for the second one is 0, then we can achieve the stable consensus. Otherwise, in case of double integrator without a controller, it would just go like a ramp.
So for Z1 thing, what will be the direction? There won't be direction, right?
No direction. The whole Z1 axis will be the continuum equilibrium points, because if Z2 equals to 0, then that will give you Z10, 0. That will be the whole trajectory, right? So this entirely, like all of them will be the series of points, as well as this is the trajectory as well as the equilibrium
Why
points.
will be the trajectory of that initial?
So that's why it is a case of the called equilibrium subspace. Do you have any doubt that how did I get this solution? Then I can show you that is how we have got this. Anyone? Any doubt? Kanika? Have you found? How we can get it? Needed the Z dot, that is in this case A bar Z, where A is this one. Then what will be the solution of Z? E to the power A bar T Z0, right? By that we have got it. So here, what will be your solution? Z of t e to the power A bar t Z0, right? Now in this case, right, that much we have to find. So e to the power at means I plus at plus a square by 2 is a square t square by factorial 2, like that. So this is I plus at plus 1 by factorial 2 a square t square. Let us break the terms. Is it now clear? like this, the case 4, that is the case of complex conjugate eigenvalues, that treatment is different from whatever we have learned, because for that we have to convert into the polar form, because converting into the polar form will help us to draw the phase trajectories. Before that, you please check all the cases which we have dealt with so far. If you have any doubt, please check your notes and check all the cases. I hope stable node, unstable node, saddle point, you shouldn't have any doubt regarding that, because those have completely unique guidelines how to draw the trajectories, and there was no confusing cases. I believe the confusing case can happen like if the continuum equilibrium point comes. So that's why although there is each case I took individually, but still, I believe there is this case of continuum equilibrium points, you may have some further confusion. So if you have any, please ask me now, or like if you have later, then also feel free to ask me. Tell me whether as of now this is fine or not. After completing the phase plane, we will start the bifurcation. So there we will take up a plenty of examples. Then that is the entire concept will be further clear to you. Because as of now we haven't solved numerical examples. So that's why you may still have some doubts, that is how to tackle the problems. But don't worry. Immediately after this, we will start from next week bifurcation. There we will take up the different type of examples, and at the same time limit cycle will also come into the picture. You please check all the classes you missed later. If you have any problem, ask me. Now you see, this is the case 4 of complex conjugate eigenvalues, right? If for any complex conjugate eigenvalues, that is, we can express the matrix in this format. A alpha minus beta, beta alpha, right? Now here the problem is, you have already seen, that is, if you have to draw the phase plane trajectories, you need to have explicit solution of the Z1 and Z2, right? But so far, whatever may be the patterns, we never had, that is, had to handle too much of coupling. But this is for the first time where it is completely coupled, right? Completely coupled means for both the Z1 dot and Z2 dot, you have contribution from both Z1 and Z2. So that's why, that is, you have to, it is not at all impossible to solve these two differential equations. But the main motivation behind phase plane analysis is that without explicit solution of the differential equation, that is, we need to proceed, right? So that's why, are you understanding what I am saying? That is, in this case, if you have to draw the phase plane trajectory, then you have to find out the solution of Z1t, Z2t. That is not very easy. Why? Because this time, that is, you have both of them, that is the coupled differential equation. Like for Z1, you have contribution from Z2. Similarly, for Z2 dot, you have contribution from Z1. If you see all the previous cases, there the A matrices was in a very much sizable way. That is, either it was like lambda 1 0 0, lambda 2, or even like lambda 0 0 0, or even like lambda k 0 lambda. In that way, that is maximum coupling we handled like this, lambda k 0 lambda. This is the maximum coupling we faced, right? Are you getting what I am saying? That is, so far the cases we have handled, there we have mostly either decoupled or maximum coupling with respect to x1, which came from the other axis or other variables. But now the case is that both of them are coupled. That means Z1 dot, it has the contribution from Z2. Similarly, Z2 dot, it also has the contribution from Z1. That is, this is a fully coupled set of differential equations. So solving them is not very easy. Again, I am saying it is not at all impossible. That is, we can really check any book of differential equation and we can proceed to solve it. But in that case, since some more mathematical calculations would be required, the main motivation behind the phase plane analysis will go off. So that's why in this case, that is, we are now going to transform this coordinate. Still it is a Cartesian coordinate. We will convert into polar coordinate, and then you will see that it will become independent of each other. That means from this Z1, Z2, we will proceed to r theta coordinate. I hope all of you know about r theta coordinate, the polar coordinates, right? So that is the requirement. Have you understood? That is why in this case we need to go to the polar coordinate. My Z1 dot r dot cos theta plus minus r sin theta, right? Minus r sin theta, theta dot, isn't it? And Z2 dot r dot sin theta plus r cos theta, theta dot, right? Let's see if we can handle them. this space, so that's why I am just rewriting these two equations here. Now we have to first substitute z1, z2, z1 dot, z2 dot, and then we'll have to like group some of the terms and we have to keep on simplifying. Okay, you start, I am also going to. What did I say? You have to first replace all the z1, z2 and their dot terms by this r and theta. Okay, and then we have to group the similar like terms and then we have to keep simplifying. Okay. So if I start from the first equation, that is this is 1, this is 2. So I'm starting with 1. Z1 dot, so that is r dot cos theta minus r sin theta theta dot equals to alpha z1. So alpha r cos theta minus beta r sin theta. Right? That is one. And then if I make any mistake, please feel free to tell me. And then z2 dot. So it is r dot sin theta plus r cos theta theta dot equals to beta z1. So beta r cos theta plus alpha r sin theta. फायस मिल क्या हुआ? फिर से understood that is why did I do this, because you see in both these equations you have this r dot minus alpha r common in the left hand side and in the right hand side theta dot minus b. That was the trick. Is it fine for all of you? now clear for all of you? Please check that this inward logarithmic pi whether does it correspond to that solution. Please look at it carefully, think, and then you ask. अभी भी तुम जाने के बाद और क्लास नहीं हुआ, उसी दिन पूरा खत्म हुआ, पर फ्राइडे में ले नहीं पाया। I will explain, don't worry. First you try to understand. I hope the mathematical derivations are all clear up to this. So from that, have you now understood? That's what we wanted, the decoupled solution of them, but which was not possible in the Z1, Z2 axis. That is the reason why we transformed that axis into the polar. Now you see, that is, we have like the decoupled equations with respect to r and theta. R dot this one, theta dot this one, right? And then like we can readily write their solution as if it is x dot equals to alpha x. Then you would have immediately written that it is x0 into e to the power alpha t, right? That's what I have written. And for theta dot equals to beta, since it is a constant, of course this will be the solution, the theta 0 plus beta into t. Now the case is that there is when I drew that trajectory, it is called a logarithmic spiral, and of course for alpha less than 0 the direction would be inward. If alpha greater than 0, then it would be outward, right? Now we have to see whether this corresponds to this one or not, right?
So how can you draw it in the clockwise sense? Like
Right,
can we
right.
write
That's right.
anti-clockwise?
Let's try to understand, that is how did we get the shape. So the solution is RT equals to R0 e to the power alpha t, right? So in that case, this will be my solution. That is, if alpha is negative, take R0 negative, R0 1 and alpha 0, alpha less than 0. Okay, we can also consider that is as if theta 0 equals to something. I still don't know that is what value I have taken, maybe 45 degree. So this is the solution for R0, or it will be simply 1, so e to the power, and alpha, let's say that is also minus 1. So then e to the power simply e to the power minus t. So then if you check the values of R, then how does it evolve? 1, 0.9, 0.8, I mean all the values continuously. I am only taking a few of them. Starting from 1, it will decay to 0. Okay? So that's why, that is like finally, whether it is clockwise or anti-clockwise, but it would be inward. What have you understood? Because if it is not inward, then the radius vector will not decay its value. That is the reason. RT equals to R0 e to the power alpha t. Now for alpha negative, the values of R, it is continuously decreasing in an exponential manner, right? So that is the reason why, that is, from wherever you choose, finally it would be inward. We still don't know in which direction it will go, but the reason behind inward spiral is that only in that case the radius will keep on decreasing, right? And then that is, it is like you have a, suppose you have a pen whose radius is decreasing, and then like it is a continuously phasor. Usually in the case of phasor, the magnitude will always remain the same, but just it's an analogy. If you think about a phasor whose radius is also decreasing, then what would happen? Continuously, that it is not a circle. Although it looks like circle, but it cannot be circle because the radius is continuously decreasing. So that's why it is a spiral.
So here beta is less than 0, right?
Here,
Beta is less than 0.
huh?
What
check from the solution, that is when it is clockwise and when it is anti-clockwise.
If beta is greater than 0, then it is anti-clockwise.
Huh.
So alpha less than 0 is a sufficient condition that it converges to a
Exactly. So it is like the alpha represents the the real part of the pole.
real part of it.
So for alpha negative, always it would be a inward spiral. Okay. For alpha positive, it would be outward spiral. Then, so this is called the stable focus. And if alpha is positive, then the shape will remain exactly the same, but the arrows would be like, then it would be diverging. It is called unstable focus. And if alpha equals to 0, then of course you would be getting a,
Circle.
we should not say circle because it means a closed curve.
Disc, a disc.
No, not disc. Because disc means the inner surface is also included. It is just the periphery. You think about that is if alpha is 0, there is no decrement in the radius. So it would be whatever shape you get, like of course if it is in the Z1, Z2 plane, it would be a circle, but when we will transform that to X1, X2, then it would be a cramped circle. It can be an ellipse, it can be any other type of shape. Okay, but please remember, always it would be a closed curve. What I wanted to mean, that is from this X1, X2 axis, if you transform back to X1, X2, then mostly you will find like this.
So it is stable.
This is for alpha equals to 0.
It is stable.
Purely marginally stable, plus minus j beta. So this is the case like this. Plus j beta minus j beta. So here if you put alpha equals to 0, then what would happen? RT equals to R0. So there is no question of the decreasing radius, right? So you won't get a spiral. It would be only one closed curve. Corresponding to 1 R0, you will get only one closed curve. So this is actually called the center case, when you get only one closed curve. And this is stable focus. If the arrows are like to outward diverging trajectory, then it would be unstable focus. Okay.
So what do you mean by converting the variable Z1, Z2 to X1, X2?
That means it is also similarity transformation, right?
Similarity transform.
If you remember at the beginning, that is we diagonalized the system. Originally it was in the X1, X2, but there it was coupled. We transformed the X1, X2 to Z1, Z2. If you remember first day.
Jordan or diagonalized. And then we are taking back to the original form X1, X2.
If you see the first class where the x1 dot x2 dot, we started with x dot equals to ax. Now a can be any arbitrary form, but we cannot proceed with that because the same problem would have happened. If they are coupled differential equations, we cannot straight away write down their solutions, right? That is the reason why we diagonalize the system. So from x we transform to z. And whatever analysis we have learned, that is with respect to z. And easily we can like transform them back to x. That is not a big deal. So that's what, if you remember in maybe 1 week or 2 weeks ago, I wrote on the WhatsApp group, that is you in the book you check, that is for all the trajectories what would be the transform version, that is what would be their change in shapes when they are transformed back to x1, x2. So once again, here if alpha is negative, then it's a inward spiral, which is called stable focus. So the 0, 0 is still the equilibrium point, isolated equilibrium point, and it's an attractor. Why? Because the trajectory is spiraling inward. So this is a step, of course, is the asymptotically stable case, and this name is stable focus. For alpha greater than 0, exactly the same pattern would be followed starting from, so then we have to take the initial condition, some part here, and then it would go spirally upward. All of you please look at the board, Moina. So if you consider any of the initial points, say for example here, then what will happen? Starting from continuously it will spiral upward, spiral out. Okay, that is for alpha greater than 0. And if alpha is equals to 0, then your radius will remain fixed for all t. There is no increase or decrease in the radius, so then you will get only one closed curve. If it is Z1 Z2 plane, it will be a perfect circle.
Why will it be a perfect circle?
No, perfect. Okay, right. Perfect circle would be there. That is, if you consider both of them to be one. Otherwise, it would be closed. That's what I said. It would be closed curve. Both of them means originally, if you see the equations, this one, then here, that is suppose alpha 0, and then so depending upon the beta, the shape would be decided, right? But always it would be a closed curve. That is, I shouldn't have said that it's a perfect circle, because the perfect circle would depend on, if beta equals to 1, then I believe it would be a circle, right?
Otherwise, it's
ellipse. For different values of beta, the shape will be different, but anyway, it will always be a closed curve. And what is the theta value? The theta is the angle subtended by this phasor or this radius vector. Now this is the theta 0 initial value. Now you see here the clockwise means it is decreasing. So if we take beta to be negative, then starting from theta 0, the angle will continuously, it will start becoming, the angle will start decreasing, and after some time, that is after compensating the theta 0 amount, it will be negative, right? But there is no end. Theta 0 plus beta into t. It will be continuously, that is, whether it is increasing or decreasing, there is no end. Continuously it will keep on taking the values. So that's why if the beta is negative, then of course for this one, that is what, alpha less than 0 and beta less than 0. The same pattern would have been taken, but in the opposite direction if beta is positive. Okay. And as I said, for alpha equals to 0, then it would be a closed curve. In some cases, it can be circle, ellipse, or any other shape, but the main thing is it would be a closed curve, which is called the center case. Center case corresponds to pure marginal stability. Or rather, here you have seen that even within the subcategory of marginal stability, we have got three cases. That is, one is the case when you have the zero eigenvalues, right? That is also a marginal case. This one is another marginal case, right? And the saddle point also, that is not marginal, but still we consider it because saddle can help you to get into a stable zone depending upon the initial condition. That's what we have seen from phase plane trajectory of simple pendulum. One day we were discussing, and then that is, you might have seen, that is where you have the series of isolated equilibrium points, and every pair of stable loci is separated by a saddle point. Just last 2 minutes. clear for all of you? This diagram is given in all the books. If you see Khalil slotting everywhere, but probably at the beginning or even in last week also, we didn't understand how to interpret. Now, can you interpret? So, every pair of stable foci is separated by a saddle. So the trajectories for the saddle, all of you please look at the board. Like this is called separatrix. Why separatrix? Because they are separating out the region. Region means, now if you see, if you take any initial condition within this zone, they will be attracted towards this point. But if you take any one beyond that, suppose if you take here, it will go like this. If you take any point here, it will go like this, or it will even, it can go like that. So this is called the zone of attraction. That is for entirely within this region. If you take any of the initial condition, they will be attracted towards this. Similarly, here also. This is the region of attraction for -2 pi, 0. This is the zone of attraction for the 0, 0. Similarly here also. This is the zone of attraction for +2 pi, 0.
Sir, here the zone of attraction is basically a circle of radius pi, right?
In Nana.
Can you see that?
So at saddle point, it can be randomly.
If it is on the saddle point, right? So perfectly, if you take an initial condition on the saddle point, then it will follow like this. If there is no perturbation, then if it is on the stable saddle trajectory, that is in the saddle, always you will find one converging, one diverging. So if it is on the converging, so it will come and stay here.
On
But
saddle point itself.
But in the physical system, there will be always some disturbances or something. So that's why, in case of a simple pendulum, never, that is, it will happen. That is, it will come and remain there. Then this point is -π0, right? Unstable equilibrium point. But it is never possible. That is, without any external support, the pendulum will remain there as it is for all subsequent time.
The direction of the small perturbance determines the upcoming stability.
That in which zone it will go. Somewhat it is either go this side or along this side. And then if you choose from this anyway, the motion is towards that. If you take this, the motion is like that. So that's why these lines, they are all other, these curves, they are called the separatrix. Separatrix means it is which separates out two regions of different properties. So in this way you can see there the region of attraction, they are separated, right? So this is actually like many of you ask me that if you have multiple equilibrium points, then what will be the nature? Then like that's what I said. Although that is in between, once or twice I tried to explain, I drew this graph and wanted to explain, but maybe it was not completely convincing for all of you, because for that we need the genuinely sound knowledge for all type of S-plane trajectories. Now you can understand. अच्छा विकी कैसा लगा? अभी पूरा क्लियर हुआ? कनिका वो सिर्फ वो वीक से काम नहीं होगा, वो केबल लेना पड़ेगा. Now I insist all of you to check these face portraits for the simple pendulum using the MATLAB simulator. Because otherwise I know that is at this moment it seems that it is 100% okay for all of you, which is not. Maybe you have got up to 80%, 20% is still remaining. So you, like this evening itself, that is you try to sit with your computer, and this is just you have to develop the equation, or equation is also given in both the Collins and Slotkin book. Just you have to simulate them and use the XY graph to check that what is the trajectory. You choose different initial conditions and then you see that is how, whether it converges, whether it is converge or diverge. Okay? One day Mithi asked that is, can we ever have a situation where two stable focus or two stable foci or two stable nodes are separated by a zone? In this case that would never be possible. In that is a particular case. Maybe one day I drew that it was for a buck converter. Then if two stable nodes or two stable foci have to be separated out, then each of them is asymptotically stable. Then if one stable equilibrium point has to switch, then definitely you need an external pulse or external input, right? And in that case, you should have a unstable limit cycle in between. That is also really an exciting case. We will learn that. After learning the limit cycle, I will show you that. Here, like all these stable foci, they are separated by saddle, and you have understood the reason. But now you see, if this is a stable focus, this is another stable focus, then the in between a saddle cannot be there. Sorry. That is what happens. That is like suppose both of them are stable node. And then what happens, that is like two stable nodes in between, and that too within the same operation. It is continuously going back and forth. That is not possible in this setting. Like I gave you the example of buck converter, where for switch on and switch off, you will be getting two different modes of operation. And then ultimately the voltage is the output voltage is the average of the entire thing, right? So buck converter means step down chopper. So for that is finally you will be getting the V0 equals to 1 by T integration Vt dt, right? So for switch on, you will have one particular set of action. For switch off, another particular set of action. Ultimately the output voltage is the average of the entire thing. So there, purposefully, we are switching that circuit from one stable condition to other stable condition, okay? And it cannot stay in between. In that cases, like here initially, that is I framed it like that, like no two stable foci cannot be separated by a saddle point. The thing is exactly not like that. It is in that case also two stable node or two stable foci, but they cannot be in between. Like if it is a saddle point, it can be in between. But in case of power electronic converters, nothing cannot be possible in between those switch on and switch off. It is only two modes, either switch on or switch off. So in between, then in that case, how these two zones would be separated? It should have an unstable limit cycle. That means in between nothing can happen. So at this moment we don't know limit cycle, so that's why you were not able to understand, but that will also be an exciting case. We will learn next week. Okay guys, thank you.